It's good to see all of you this morning. This is now the 5th annual review of the Nobel Prizes, and it's been well received before, and hopefully this one will too. I want to thank the library here, and especially Deb, because this morning there's been a scramble to sort things out just on which network is up or down. So let's just pray that everything holds for the next hour. I do want to thank, right out of the gate here, Velme and David Elkins, because I'm giving the first 3 talks, today on physics, next week on chemistry, doing economics then, and the Peace Prize, and Velme Elkins is doing literature. So, so they're half the Nobel team. I feel like I'm in an airplane right now because I have 2 kind of cockpit sources of information now. So I'm really talking from an iPad on my right. So there are some sources, and I'll just move on to this, see if this comes up or move it. Some of them are pretty, I just can't get the next ones here. But anyway, the sources, the only thing unusual about it, I mean, 2 of them are from, well, 3 of them are from the UN, but I included the papal encyclical on climate change because in our church, we did this several years ago, and quite aside from the church side of it, it was very well done on climate, and that happened to coincide with the Paris climate meeting. So that's actually a very good source. Now, just a little bit on previous Nobel Prizes. And this is one that the first physics one that I did, and this was 5 years ago, 2017. And here are the 3 recipients. I think 2 of them were in their 80s. 2 of them this morning are 90. So age is okay. Certainly I feel that way, but these 3 people led the charge, Rainer Weiss and Barry Barish and Kip Thorne, in developing a device to pick up evidence of gravitational waves. Now, it's an outcome of Einstein's theory of general relativity that if something big happens in the universe, it might rile or roil the space-time continuum, and that might be detected by some device to pick up these ripples in space-time. And they succeeded in 2015, and then got the Nobel Prize for it 2 years later. I highlight this partly because this was a project that lasted over 30 years. That meant that, I think I did my sums this morning, that was 8 presidents. And a lot of senators changing and members of the House, and yet they had continuous funding. That was remarkable to me. I don't know whether that could be sustained these days. Just the next slide really shows the. Now this is not an actual picture. It wasn't until 2 years ago that we actually saw a black hole, but here's simulated. 2 of them doing a close dance just before they merged, and they were pretty massive, not as massive as the one at the center of the Milky Way, but 36 and 29 times the mass of our sun, so pretty big. And then just moving along to last year's Nobel laureates, and 1 theoretical physicist. Roger Penrose in the middle, and 2 practical, or might say laboratory-based Nobel laureates, Andrea Ghez and Reinhard Genzel. They led 2 independent teams, one in Europe, the UK linked in there too, and the US. But both teams had the same goal, and that was to identify clear evidence for a giant black hole at the center of our galaxy, the Milky Way, and they managed to do that. Roger Penrose, on the other hand, a theoretical physicist, provided mathematical evidence for the shape, what shapes a black hole. And so it was an interesting Nobel Prize last year. One added point in there is that Stephen Hawking missed out because Roger Penrose and Stephen Hawking were buddies and sometimes worked together, sometimes argued about things, but nonetheless worked on black holes. And had Stephen Hawking still been alive, it would probably have been a joint Nobel Prize shared between the two. I don't know that, but my guess is that's true. Well, this year, here are the three. Now, I don't know who the artist is that works for the Nobel group, but it seems to be the same one because everyone seems to look the same every year. But the three of them, Sakuro Manabe and Klaus Hasselmann. I think Klaus is 89 and Sakuro is 90. And Giorgio Parisi is from Italy. And we'll talk about him later, but I think he's 73 or 74. So we're talking this morning about climate change, here now and worse coming. This year's Nobel Prize in Physics represents a timely change. No black holes, no gravitational waves, no question about the birth of the universe, no laser tweezers, and no new particles, accompanied by the usual inflationary claims that without this or that particle, think about the Higgs or God particle here, there would be no universe and no life. The physics award this year wasn't quite so dire as the particle hype, but the tone struck by climate scientists in documents they prepared for the United Nations, and they're in the list that I gave you, in the run-up to the UN summit in Glasgow, and we're now into the second week, was worrisome and even ominous. The evidence is clear. Climate experts agree. Human-created climate change poses a clear and present danger for life and what you might remember Carl Sagan so famously once called our beautiful pale blue dot. Unless we put the brakes on our consumption of fossil fuels and other human-sourced greenhouse gases, the livelihood and survival of humanity and countless other species will be in serious jeopardy. They already are. But within this century for most, if not all, and for sure the next. Now, the Nobel Committee this year made a statement in choosing these three scientists whose work laid a solid foundation for climate science. In the words of the Nobel Committee, go back on that. In the words of the Nobel Committee, prize went to Sakuro Manabe and Klaus Hasselmann for the physical modeling of Earth's climate, quantifying variability, and reliably predicting global warming. That's what this prize, half of the prize, is all about. The other half is an interesting departure. Giorgio Parisi, an Italian physicist, quantum physicist, for the discovery of the interplay of disorder and fluctuations in physical systems from atomic to planetary scales to climate. Now that sounds really far out, but it isn't. Climate is enormously complex. There are a lot of moving parts, and so this is important light to be shed on the subject. So climate science is on solid ground despite vocal and often politically charged climate change deniers. Despite the fact that climate has so many variables and moving parts, Manabe and Hasselmann developed some of the earliest reliable models for longitudinally assessing trends in climate. It was precisely because of those many variables, moving parts, as I said earlier, and apparent chaos that Parisi's work was so important, because he shed a light on how highly complex systems such as climate can be meaningfully assessed. Thor Hans Hansen, the chair of the Nobel Committee for Physics, it's unusual for that person to say something, said, the discoveries being recognized this year demonstrate that our knowledge about climate rests on a solid scientific foundation based on rigorous analysis of observation. So solid and rigorous, those are the two words, the operative words. They found hidden patterns in the climate and in other complex phenomena. All complex systems consist of many different interacting parts. I've already said that. They have been studied by physicists for a couple of centuries and can be very difficult to describe mathematically. They may have an enormous number of components or be governed by chance. They could also be chaotic, like the weather, where small deviations in initial values result in huge differences at a later stage. This year's laureates all combined to contribute to us gaining a much better understanding of such complex systems. Sakura Manabe demonstrated how increased concentrations of carbon dioxide in the atmosphere led to increased temperatures on the surface of the Earth. So that's key. That's the footstone. In the 1960s, he led the development of physical models of the Earth's climate. Now, that's in an era when computers were really pretty primitive, and was the first person to explore the interaction between radiation balance and the vertical transport of air masses. I'll say more about that later. His work laid the foundation for the development of climate models. About 10 years later, Klaus Hasselmann, a German, created a model that linked together weather and climate. That's a really important linkage. He also developed methods for identifying specific markers, if you like, fingerprints, that identify a causal factor as either natural or human, of human origin. Now, around 1980, Giorgio Parisi discovered hidden patterns in disordered complex materials. His discoveries are among the most important contributions to the theory of complex systems. Now, let's get on with the greenhouse effect. Well, greenhouse effect, we usually hear about it in a bad way, but life on Earth wouldn't be what it is these days without a greenhouse effect. 200 years ago, the French physicist Joseph Fourier studied the energy balance between the sun's radiation toward the ground and the radiation from the ground. He understood the atmosphere's role in the balance. At the Earth's surface, the incoming solar radiation is transformed into outgoing radiation. We now know infrared or dark heat, which is absorbed by the atmosphere, heating it. The atmosphere's protective role is now called the greenhouse effect. That name comes from its similarity to the glass panels of a greenhouse, which allow through the heating rays of the sun, but trap the heat inside. We certainly know about that around the Niagara region. However, the radiative processes in the atmosphere are far more complicated than any greenhouse. The task remains the same as that was undertaken by Fourier to investigate the balance between the shortwave solar radiation that comes to our planet from the sun and Earth's outgoing longer wave infrared radiation. The details were added by many climate scientists over the following 2 centuries. Contemporary climate models are incredibly powerful tools, not only for understanding climate, but also for understanding the global heating for which humans are responsible. These models are based on the laws of physics and have been developed from models that were used to predict the weather. Weather, well, as a sometime pilot, I'm certainly very aware of weather, that nothing is much predictable beyond 12 hours or 24 hours. But anyway, weather is described by meteorological quantities such as temperature, precipitation, wind, or clouds, and is affected by what happens in the oceans and on land. Climate models, on the other hand, are based upon the weather's calculated statistical properties, such as average values, standard deviations, highest and lowest measured values, and so on. That information cannot tell us what the weather is going to be like in Niagara on the Lake on January the 10th, but it can give us a rough idea of what the climate might be for the whole month in January. Establishing the role of carbon dioxide. The greenhouse effect, as I mentioned earlier, is essential for life on Earth. It governs temperature because the greenhouse gases in the atmosphere, carbon dioxide, methane, natural, and now human generated or cow generated, water vapor and other gases, first absorb the Earth's infrared radiation and then release this absorbed energy, heating up the surrounding air in the ground below. Greenhouse gases actually comprise a very small proportion of the Earth's dry atmosphere, which is largely nitrogen and oxygen. Together, these comprise, the latter two, 99% by volume of the atmosphere. On the other hand, carbon dioxide, the big villain, comprises but 0.04% by volume, but it has an outsized effect. The amount of water vapor in the atmosphere depends to a great degree on temperature, leading to a feedback mechanism. More carbon dioxide in the atmosphere warms it. That allows more water vapor to be held in the air, which in turn increases or magnifies the greenhouse effect and makes temperatures rise even further. If the carbon dioxide level drops, some of the water vapor will condense and the temperature will fall. An important first piece of the puzzle about the impact of carbon dioxide came from the Swedish researcher and Nobel laureate Svante Arrhenius. Incidentally, it was one of his colleagues, meteorologist Niels Ekholm, who in 1901 was the first to use the word greenhouse in describing the atmosphere's storage. Arrhenius understood by the end of the 19th century the physics responsible for the greenhouse effect, that outgoing radiation is proportional to the radiant body's absolute temperature to the power of 4. That's quite a magnification factor. The hotter the source of the radiation, the shorter the ray's wavelength. The sun, for example, has a surface temperature of 6,000 degrees centigrade, and as a result, primarily emits rays in the visible spectrum. Earth, with a surface temperature of about 15 degrees centigrade at sea level on a standard day, re-radiates much longer wavelengths in the infrared range, which are invisible to us. If the atmosphere did not absorb the latter radiation, the surface at the temperature would barely exceed minus 18 degrees centigrade. Actually, an interesting sidelight here, Arrhenius was actually attempting to work out what caused the recently discovered phenomenon in his day, ice ages. He arrived at the conclusion that if the level of carbon dioxide in the atmosphere halved, this would be enough for the Earth to trigger a new ice age, or flip it, vice versa. A doubling of the amount of the carbon dioxide would increase the temperature by 5 to 6 degrees centigrade, a result which would fortuitously was astonishingly close to current estimates. Well, let's get to R3. In the 1950s and 60s, in the 1950s, Sakura Manabe, he moved from Tokyo to the United States, and that's where he developed his career. And the aim of his research, like that of Arrhenius around 70 years earlier, was to understand how increased levels of carbon dioxide cause increased temperatures. However, while Arrhenius had focused on radiation balance, Manabe led work on the development of physical models to incorporate this vertical transport of air masses due to convection. To make these calculations manageable, if you think about this, the 1960s, crude computers and all of that, he had to simplify the model. He chose to reduce the model to a vertical column rising 40 kilometers up from sea level. Even so, it took hundreds of valuable computing hours, imagine paying for it, to test the model by varying the levels of gases in the atmosphere. Now, the most important thing here is that, and we'll talk about this figure in just a second, but oxygen and nitrogen have negligible effects on surface temperature, while carbon dioxide has a clear impact. When the level of carbon dioxide doubled, global temperature increased by over 2 degrees centigrade. That's what all the buzz, or much of the buzz, has been about the last week. in Glasgow. So this is a figure, and I borrowed this directly from the committee because it's their figure for illustrating the phenomenon. So let's just work with that. And the sun on the left and coming in, incoming visible light, and that it's transformed, the reflected light is of a longer wavelength, infrared, and some of that heats up the atmosphere and the earth, and some of it escapes out of the atmosphere. And warm air is lighter and can hold more water, so it picks up more water vapor increases. I remember I mentioned that magnifying effect of water vapor earlier. So there's the model. This figure illustrates that incoming solar radiation. Now let's move along to, well, this one. A bit of a messy slide, but let's work with it. This figure showing our average temperatures from each decade compared with the 20th century. So this is 1900s to 2000s. All right, so 1900s upper left, our decade lower right. Now, this is it shows it pretty obvious, a warming trend. Now, this is a warming trend of oceans. What you're seeing are oceans. And the oceans absorb a lot of carbon dioxide. That's not a good thing necessarily because it acidifies the oceans. It has its impact, but it also warms the ocean. So that the oceans and seas kind of buffer the earth. Now, let's just move along here and to our next one because, oh, well, that's interesting. Let's see. Well, you know what? We can live with that. What I'm going to say here, for some reason, yeah, back we go. It's pretty obvious if you look at global mean surface temperature that has increased over the last since the Industrial Revolution. So beginning in the late 1700s and right up to now. But that the slope of that has certainly increased much more steeply in the last 20 to 30 years. And interestingly enough, the same is true with carbon dioxide levels. In fact, for carbon dioxide, it's quite possible to look back thousands of years, hundreds of thousands of years, even a billion years. And so you can see these glacial periods, interglacial periods. We're in an interglacial or warm period right now. But what's obvious when you look at the CO2 levels, they may be zigzagging up and down through these glacial and interglacial periods, but then it changes. It changes in the last, say, 100 years, especially 50 years, but a little bit before that. Nothing like what's been happening in the last 50 or so years happened before in the last 500,000 or even million years. So this is new. Now let's go along. Now this is an important one. So we'll march through this one a little bit. This is Manabe and one of his graduate students or team, and plotting the effect of carbon dioxide on temperature from the base of his model, which is at sea level, up 40 kilometers high. Now, if you think about it, most commercial aviation is taking place well under 20 kilometers. So a lot of this is stuff we're not flying in, and I would be right near the bottom here. So, so this figure compares the temperature of the atmosphere from sea level to 40 kilometers high, related to different concentrations of carbon dioxide, ranging from low, 150 parts per million. So that would be kind of the blue, medium, 200 parts per million. So that I think it's the black, and high, the 600 parts per million, and that's red. Now just look what happens to red. all the way up to maybe, almost 20 kilometers up. The higher carbon dioxide level resulted, relative to the other concentrations, a higher temperature in the atmosphere. But above that, it's the reverse, it flips. And the higher concentration of CO2 is now results in a lower relative temperature to the other concentrations of carbon dioxide. That is the fingerprint of CO2 on the atmosphere. That's the evidence. That's the strongest evidence. So the data clearly illustrate that while CO2 heats the lower levels of the atmosphere, it cools the atmosphere at higher levels relative to normative temperatures and altitudes. The model confirmed that the heating really was due to the increase in carbon dioxide because it predicted those rising temperatures at the lower levels and that reversal in the higher levels. Now let's deal with weather as chaotic. About 10 years ago, about 10 years after Manabe-Hasselmann succeeded in linking weather and climate. I mentioned that much earlier, by finding a way to, as the language goes, outsmart rapid and chaotic weather changes that are so troublesome for calculations. Our planet experiences big shifts in weather because solar radiation is so unevenly distributed, both geographically and over time. For example, the Earth is round, so fewer of the sun's rays reach the higher latitudes than lower latitudes. Not only this, but the Earth's axis is tilted, and that produces the seasonal differences in incoming radiation. And the differences in density between warmer and colder air cause colossal transports of heat between different latitudes, between the ocean and land, sea breeze, land breeze, think that, and between higher and lower air masses, which drive the weather on our planet. As we all know, making reliable predictions about the weather for more than a few days is a challenge. 200 years ago, the renowned French scientist Pierre-Simon Laplace stated that if we just knew the position and speed of all the particles in the universe, it should be possible to both calculate what has happened and what will happen in our world. And in principle, this should be true. Newton's 3-century-old laws, for example, of motion, which also describe air transport in the atmosphere. But they're entirely deterministic. That is, they're not governed by chance. However, nothing could be more wrong when it comes to the weather. This is partly because, in fact, it is impossible to be precise enough to state the air temperature, pressure, humidity, or wind conditions for every point in the atmosphere. Also, for those of you with a mathematical bent, the equations are nonlinear. That is, small deviations in initial values can make a huge difference further out or longer out. So that was the butterfly effect. In practice, this means that it is impossible to produce long-term weather forecasts. The weather is too chaotic. This discovery was made in the 1960s by an American meteorologist, Edward Lorenz, who laid the foundation of today's chaos theory. Well, so how do you, if weather is so unpredictable, and a lot of the data that supports weather analysis is equally seemingly chaotic, then how do you sort out stuff on a much longer scale? Around 1980, Stochastic demonstrated how chaotically changing weather can be described as noise, thus placing long-term climate forecasts on a firm scientific foundation, kind of background noise that kind of evens out. Might get a trend from it, but it evens out all those little minor fluctuations. Furthermore, he developed methods for identifying human impact on the observed global temperature. As a young doctoral student in physics in Hamburg in Germany in the 1950s, Hasselmann worked on fluid dynamics and then on ocean waves and currents. He moved to California. I don't know whether he was a boarder or not, but anyway, he moved to California. He met one of his good friends, or man who became a good friend there, was Charles David Keeling. And Keeling is legendary. There's the curve, the Keeling curve. And it plots carbon dioxide going back to 1958 from a site in Hawaii. And look at the trend. I mean, gee, there's not a lot of standard deviation there. It's just right up, steady up from 1958 to the present. So that Keeling curve is often quoted by climatologists. Well, let's move along. Now, obtaining a climate model from noisy weather data can be illustrated by walking a dog. A lot of people in Niagara-on-the-Lake have dogs, so you'll be right with this one. The dog runs off the lead, backwards and forwards, side to side, and around your legs. How can you use the dog's tracks to see whether you are walking or standing still, or whether you are walking quickly or slowly? The dog's tracks could be likened to the changes in the weather, and your walk to the calculated climate. It's an interesting exercise in your head. It's one of those mind games. Like that was Albert Einstein's analysis of Brownian motion. And he came down to imagining trying to track a drunk starting at a lamppost and lurches this way and that way and this way. Is there a mathematical way of determining where the drunk will be at a certain time? So that's interesting. Well, never mind the dog or the drunk. Is it even possible to draw conclusions about long-term trends in climate using chaotic and noisy weather data? Hasselmann created a stochastic climate model, which means that chance is built into the model. His inspiration, by the way, came from Albert Einstein's theory of Brownian motion, which I think is one of the cleverest things, actually, that Einstein did. In 1905, it was one of his 4 great papers in 1905. So using this theory, which he admits he based on Einstein's work, he demonstrated that the rapidly changing atmosphere can actually cause slow variations in ocean and land temperatures. Now, what about discerning the traces of human impact? Once the model for climate variations was finished, Hasselmann developed methods for identifying human impact on the climate system. He found that the models, along with observations and theoretical considerations, contain enough information, more than enough information, about the properties of noise and signals. For example, changes in solar radiation, volcanic particles, or levels of greenhouse gases. They all leave unique signals or fingerprints in the data. This method for identifying fingerprints can also be applied to the effect that humans have on the climate system. Hasselmann thus cleared the way to further studies of climate change, which have demonstrated, oh, there's that missing slide, but we'll skip that, those two. Now here's the crunch. This is the final one that the Nobel Committee put together, which I rather like. But anyway, it's fairly straightforward. This illustration was taken from the Nobel Committee's summary and compares natural and human impacts on global temperature relative to average temperatures in degrees Celsius between 1901 and 1950. So 1901, 1950, that's the baseline against which these measurements are determined whether they're kind of increasing or diminishing. Anyway, the effect of only natural sources. Natural sources is blue, and it's the only one going down. And it's been going down through a period when there were 3 volcanic eruptions. The ones that go up are where the contribution of human contributions to climate change, temperature and CO2 are, and the black actually represent observations, numbers, but numbers from observations. So the evidence seems very clear that you can tease out the difference between natural weather modified events and human caused events. So now this year, I said earlier, the Nobel Committee really did step out on this one in a way that I haven't seen before. And so in the words of the committee, this is what they've said. Looking at all of the evidence, and they would have seen a lot more evidence than we've seen this morning, and certainly many of the write-ups. We can no longer say that we did not know, or we can't claim ignorance anymore. The climate models are unequivocal. Is Earth heating up? Yes. Is the cause the increased amounts of greenhouse gases in the atmosphere? Yes. Can this be explained solely by natural factors? No. Are humanity's emissions the reason for the increasing temperature? Yes. Pretty unequivocal. It's very unusual for them to kind of step out of their box and say something like that publicly. And of course, this was just weeks before the climate meeting. So it cannot have been unintentional that climate was singled out for a Nobel this year and for those comments. Well, now we move along. There's Giorgio Parisi. Actually, yeah, there he is. Now look at that. Isn't that charming? You would know he's Italian almost from that picture and the surroundings he's in, and he's just been told that, or hours before, that he won a Nobel Prize. So there's a celebratory drink. It looks like milk. I'm sure it isn't. So now, by the way, he's the youngest of the lot. He's 73 or 74. Around 1980, Giorgio Parisi presented his discoveries about how apparently random phenomena are governed by hidden rules. His work is now considered to be among the most important contributions to the theory of complex systems. Modern studies of complex systems are rooted in statistical mechanics, which was developed in the second half of the 19th century by three famous physicists, James C. Maxwell, Ludwig Boltzmann, and J. Willard Gibbs, who gave it its name, statistical mechanics. It evolved from the insight that a new type of method was necessary for describing systems such as gases or liquids that consist of large numbers of particles. This method had to take the particles' random motions into account. So the basic idea was to calculate the particle's average effect instead of studying each particle individually. For example, the temperature in a gas, and this is the figure that goes along with this. So the gas is in a box. It begins in a box on the left. So, for example, the temperature in a gas is a measure of the average value of the energy of the gas particles. The particles in a gas can be regarded as tiny balls, in that figure on the left, flying around at speeds that increase with higher temperatures. When the temperature drops, or the pressure increases, the balls first condense into a liquid and then into a solid. This solid is often a crystal, where the balls are organized in a regular pattern. However, if the change in temperature happens very rapidly, the balls may form an irregular pattern that does not change, even if you make it colder or compress it, or try to compress it even more. If the experiment is repeated, the balls will assume a new pattern, despite the change happening in exactly the same way. Why do the results differ? Sounds like weather chaos, doesn't it? Understanding complexity. The compressed balls are a simple model for ordinary glass and for granular materials such as sand and gravel. However, the subject of Parisi's original work, now this is half the Nobel Prize this year, was a different kind of system, spin glass, which I didn't know about until there. Now there's a model of spin glass. And spin glass here, in this case, there are copper atoms, the green here, arranged in a regular lattice. And there are a few iron atoms mixed in with them, and iron atoms are magnetic, so they have a magnetic field, polarity to them. And in this case, they seem to be random, they associated. So spin glass is a special type of metal alloy in which the iron atoms, for example, are randomly mixed into a grid of copper atoms, even though there are only a few iron atoms there. They change the material's magnetic properties in a radical and puzzling way. Each iron atom behaves like a small magnet or spin, which is affected by the other iron atoms close to it. In an ordinary magnet, all the spins point in the same direction, but in a spin glass, they're, in quotes, frustrated. Some spin pairs want to point in one direction, others in another direction. So how do you find an optimal orientation? In the introduction to his book about spin glass, he writes, it's Parisi, that studying spin glass is like watching human tragedies of Shakespeare's plays. If you want to make friends with two people at the same time, but they hate each other, it can be frustrating. This is even more the case in a classical tragedy, where strongly emotional friends and enemies meet on stage. How can the tensions in the room be minimized? Spin glasses and their exotic properties provide a model for complex systems. Weather, for example. In the 1970s, many physicists, including several Nobel laureates, searched for a way to describe the mysterious and frustrating spin glasses. One method they used was the replica trick, a mathematical trick gimmick in which many copies or replicas of the system are processed at the same time. However, in terms of physics, the results of the original calculations are really unfeasible. In 1979, he made a decisive breakthrough. He showed how the replica trick could be ingeniously used to solve the spin glass problem. He discovered a hidden structure in the replicas and found a way to describe it mathematically. What he was essentially saying was that physical systems like this try to seek the lowest energy level. And when magnets are kind of an opposite poles to one another, it requires more energy. There's more energy in the system, but it really wants to go to a lower energy system. It wants to be more aligned. So the implication here is that what looks like a chaotic, disordered system, actually there is a form there. It's hard to recognize, but it is there. And so he discovered this hidden structure, what's called a hidden structure in the replicas, and found a way to describe it mathematically. It took a long time for the mathematics to be proven to be correct. But what turned me on with this was that I hadn't thought about this, was that it was applicable to neuroscience, and especially the brain, and to artificial intelligence and machine artificial intelligence and computer, using the brain as a model for how a computer might work and solve problems. So I can see the connection, and apparently it's been used. The same theory has been used to analyze protein structure, and in biology these days that's big. Just think about the coronavirus. We're really talking about molecular studies at almost at the micro level here, atom by atom. So his work is actually relevant. Now there's the last thing. I don't know where we are on time. All right, so I was struck just serendipitously because in preparing this talk, because there was a paper in Nature about 3 or 4 weeks ago, And just as a background for this, I will say that you're probably aware that humans originated in Africa, and probably somewhere between 150, 250,000 years ago, but that's how far back, and then dispersed into what would have been probably the Arabian Peninsula and the Middle East, and then through Europe and Asia, and eventually to reach Australia, and still last, the Americas. Well, if you talk to most people in this field in, say, 2000, the evidence seemed to suggest that the dispersal took place 65,000 years ago. That's when it happened. Now, we're not talking about an army walking across. We're talking about small nomadic bands, and many of them, and small numbers. But in the aggregate, 65,000 years ago. Well, there's a rub in that, because if you look at, let's see, where are we here? Yeah, here we are. Here's our map. If you look at this map, look at this. The arrival time in Australia is 65,000 years ago. That's obviously not sustainable. I mean, they must have been very quick on their feet to disperse out of Africa 65,000 years ago, and in the same year reach Australia. So that was genetic evidence and some fossil evidence too, that about the dispersal times. Well, anyway, and then in the last few years, the discovery that in the Levant area, the region of the Middle East where Israel is now, of Neanderthals and modern humans, some fossil remains that date, say, 100,000 years ago or 150,000 years ago. And then I think in the last year in Greece to over 200,000 years ago. So clearly humans were dispersing at earlier times. So the subject of this paper was, well, what would encourage them? What would make it possible for them to disperse? Well, then they looked at climate. So when they thought, well, when did the area, say North Africa, Northeast Africa, when was it green? When was there enough water? When were there lakes in those areas? When were there lakes in Saudi Arabia? When was there game? Those would be optimum times for humans to move. And there's almost an exact correspondence between the cycle of interglacial change and glacial change. So periods of warming, 800,000 years ago, 600,000 years ago, we're now talking about Saudi Arabia here and North Africa. And then 400,000 years ago, 200,000 years ago, roughly 100,000 years ago, and a very good match with the fossil and the genetic evidence for when at least some humans and early humans, archaic humans, disperse. So there's a nice combination or fit between climate variability and human dispersal and how we came to be who we are. So on that note, I'm going to, let me see. Oh, well, here's I rather like this one. This is a picture. It's this is an orphaned gorilla, and it's being carried by a gamekeeper, and it's in the Congo's Virunga National Park, which is under the same threat as the Amazon is. This is second only to the Amazon. These are areas to trap carbon. And the same thing is happening, cutting them down and threatening that carbon trapping. So, now, additional reading I had, so I don't think I have anything more to say on that. By the way, there is a wonderful article written by a physicist I'm trying to think of the university, but in upstate New York, on that Giorgio Parisi's work on the spin glass. It actually made sense to me. It's not part of the quote. It's not included in the material from the Nobel Committee. So with that in mind, that's the background on climate change. Now, I had a choice here to become an advocate and kind of summarize all of the bad news and the projections and that kind of thing, but I don't think that was my job today. My job was to talk to the Nobel Prize and why it was awarded and what these fellows did. But when I look at the evidence is overwhelming. And I think we're in serious trouble. We're in serious trouble if we just stay on the same trajectory we are right now and do nothing. But don't make it any worse. Allowing it to get worse really creates a conundrum. So I'm going to suggest, we're almost done. I'm going to suggest that if there are questions, that maybe you might want to email them to me. What? Okay, all right. Oh, now next week is the chemistry prize, which is a fun prize and actually works off an earlier prize 2 years before that, and so it's really good work, and it's a good story to tell. And then and the same is true of the medicine and physiology. It's more of a actually the physiology medicine prize is right up my alley this year. So so that's the next 2 weeks. And then David Elkins takes over for the economics prize, and the Peace Prize, and then Val May will end it as she did the last 3 years with the literature prize, and that's always very, very well done, as are David's. So thank you very much, and we will see you next week.
Thank
Hi,
you.
everybody. Have a nice day.
Thank you.
Thank you, Bill.